Tripathi, President of PS, Professor Paikrai, Dr. Roth, Director ITR, Dr. Naik, Director PXC, Professor Patnaik, Chairman PG Council, Dr. Agrawal, Dr. Bishwal, Dr. Mishra, Professor Chengalur, Director TIFR, respected teachers in the audience and members of the Odisha Physical Society. Ladies and gentlemen, thank you very much for calling me, although you have called me as a chief guest, but I think I am very much part of this society. And not only me and my wife Swarno, we are both are members, although we are not able to come due to the long distance. In fact, I attended the first meeting in 2017 at Berhampur University. It was organized by Professor Mishra, Sanidha Mishra, who is here. And this is organized by Professor Rida Paikrai, the president. And both happen to be my classmates. And thank you, Dr. Agrawal, introducing me. But I have another identity. That is, I am an alumni of this university. And in 2022, Professor Tripathi, with the recommendation of the Senate, they gave me honorary degree of philosophy. So I graduated from MPC College, Baripada, and my education became complete with this university. Yesterday I reached a bit early in the guest house. I was interacting with my colleagues, seniors, Professor Bhupendrath, Professor Panigrahi, Prashant Nagare, then young colleagues like Santosh, Jajati, Prakash. And after discussing with him, I found that what they are doing in the modern trends of physics. And today it was completed very nicely summarized by Dr. Roth and both Dr. Naik. And these are really the trends of physics and ballistics. And in fact today, science to some extent, physics to in particular, is being driven by what people want at large. The society also demanding that you do this. A couple of years back, I happened to meet Renuka Chaudhary, who was the chairman of the Science and Technology Committee, Parliamentary Committee. Now Joyram Ramesh is there, but she was the chairman. That is the committee gives funding to for all scientific activities. They review critically. So in some occasions, I happened to meet her. Immediately she asked how much research is going on in graphenes. Graphenes, you know, she was asking probably around 15 and 16, and the discoverer of the graphene got Nobel Prize in 2010. Graphite, carbon atoms, take one layer, the property changes. It changes so much that it becomes a wonder materials. 2D, what you now call 1D, 2D, 3D materials. This is the 2D structures of carbon atoms. The property is extremely different. Super strong, super light, having large conductivity, and it is applied in everywhere, industry, medicine, so the life is going to change. That is the demand of the parliamentarians, how much research you are doing today, and very relevant. It is for the society, and science is extremely well. In fact, Professor Rath mentioned topological electronics. You know what it is? The name may be fearing, but it's very wonderful technology. In the same materials, the bulk is the insulator, like any other insulator, but surface is conducting. That is what, and this conducting surface and the bulk insulator, they are separated by topology, cannot come from one to another, and it is a wonder. Surface is conducting and inside is insulator. That's why the Nobel Prize again given in 2016 for topodynamics discoverers. Why I am telling today that it is not only the requirements of the society, science is equally rich. Let me take an example of graphene. You know, the electrons there, graphene is now called as a semi-metal. The conduction band and valency band touch. So that electron very easily go from one, get excited to the other one. And in this process, I am doing little science in particle physics. You know, electron, it was first described by the Dirac relativistic equation. And he predicted from this equation also an antiparticle called positron. And it is a wonderful equation. But it has a mass. It is a fermion. So that equation is applicable to any fermions. But then there is a gentleman mathematician, Hermann Weyl. He, out of curiosity, just wanted to put the mass zero. and these two equations decoupled. That is called Weyl equation. And he mathematically believed that there should be a fermion, if not electron, it should be massless. And the scientists or particle physicists struggled a lot. The way they are struggled a lot to get the Higgs boson or God particle for many years. Similarly, many scientists struggle to get an electron or fermion which will be massless. Never found. And wrongly they thought neutrino could be that. It could be a massless particle, fermion. Wrongly, until in 2017, proven that neutrino has mass. Nobel Prize went to Gajita. So then all particle physicists were disappointed that they never see a fermion which is massless. But now you see graphene. Graphene electrons, it behaves like a massless electron. It is a Weyl electrons. And particle physicists, though missed this study in their early days, 50 years back, probably they can study this thing in condensed matter physics. A wonderful things. Because now under condensed matter physics or science, it is not just applied science, applied to everybody, but it is a science to do fundamental discovery. That's why it is becoming important. Alloys. Today we know elements, 92 elements up to uranium, naturally occurring. Beyond that you have to create artificially. But these elements, the composition, you can create wonderful series of materials. Alloys you all know, even I also know, because you know plutonium, which used in many ways. It is a power source. If you split a plutonium, you will get nuclear energy. And we are going to use this way. But plutonium is a wonder material. Science is very rich. People say plutonium is a physicist. It is a dream of the physicist, but it is a nightmare to the engineers. Pure plutonium, if you want to do anything, you want to make a bulb or a road, engineering you want to do, you cannot do it. You know, it is little temperature shape changes. It has just 6 allotropes. Shape versus temperature you plot. It goes very quickly, it changes from one phase to another, alpha, beta, gamma, delta, like 6 phases. And when, suppose you want to do a welding for engineering purposes, even little temperature it will take to another phase, you cannot do anything. And then there was a scientist in Los Alamos at that time, Professor Smith, he told a little bit of gallium, 3%. The moment you add that alloys, become absolutely stable. And that is why many things could be done. In fact, alloying started from those times even earlier. Today, you know, we are talking about alloying 5 or more than 5 elements. They are called high entropic alloys. Not dhatu, we must have heard our ancient technology. When Panch dhatu, when 5, 6, 7 mix, property completely changes. And we are discovering today. High entropic alloy, there are 5 elements or more than that. Property wonderfully changes, they are called high entropic alloys, you must be knowing it. These are the material science. I think another coming generation, it is the material science probably will be taking over everything. And not only that, while doing the material science, probably another direction will be opening up, understanding the basics of the nature, which we have not understood today. Same neutrino which I told you, it is there long back. As long as positron was discovered, beta decay was discovered, at the same time neutrino was also there. And we have not understood today. Higgs was discovered. Now we are looking at the gravity. It was ballistic is controlled by the gravity. It is there. But today we are getting gravitational wave. And in India, if you see, our science, those Department of Atomic Energy, Department of Space, and Department of many other departments, the way science we are supporting, the way engineering we are supporting, if you see, it is not less than anywhere. It is not less what is being done outside. Very competitive science. Gravitational wave, if you want to detect, which also a Nobel, anything you do, you get a Nobel Prize in that. And that is the facility we are setting up in India only. It is called LIGO, Laser Interferometric Gravitational Experiment. We are setting up in Department of Atomic Energy, set up square kilometer array. Probably Professor Chengalur might touch up a little bit. Again, we are driving the projects. Neutrino project we wanted to do, could not move much because it has to be underground experiment. We want to go down because it has to be cut by the cosmic radiations. So go deep, you can do that. But people in this country or many other country, people think neutrino is very dangerous. If you take into the underground, you can have anti-neutrino, probably fuse them and you create nuclear bombs. So far we never got a place and getting driven from one place to another. This type of experiment could not be done, otherwise you can do that. And as all you know, we are talking about little bit recent trends in science.